So today's the main topic of this webinar is production chunking and retrieval in vector databases. So as we all know, RAG is currently the hottest piece of technology or application right now. Whatever kind of chatbot you make, whether they are simple question answering chatbots or whether it is the helping chatbot, etc., they all have some sort of retrieval augment generation or RAG in its pipeline or in the backend. So before we go further discuss about this particular entity, something about myself. So I am Pranjalya Tiwari. I am a senior software engineer and machine learning engineer who has been working in this field for approximately 5 years and more. And I have built deep learning architecture. I have researched in building these deep learning systems, and also I have worked in putting these applications once they are trained and ready to be put into production and into the maintenance. So this was enough about me. And so we go back to the actual topic of our discussion, which is the retrieval augment generation. So what is this RAG pipeline? So this RAG pipeline is nothing. Before we discuss about what is the RAG pipeline, uh, we understand what is the use of this particular RAG entity. So whenever you are, let's say you have a corpus of document, let's say your employee handbook, and you want to build a question answering system so that people can refer to the employee handbook and get their answer immediately. In this current AI scenario, it is not possible that you have this entire 100 or 1000 page handbook to be completely fit into the context window of a particular LLM. Because as we all know, at the end of the day, the AI with the particular method which answers the question or gives us the response is the LLM, the large language model. And each large language model has a particular context window. So it is not possible for this entire huge piece of document to be fit into this particular context window. So for that, we need RAG. Does RAG do? RAG does is it first splits this particular document into n number of sections, and then while a client or a customer or a user asks a question, it finds the most relevant piece of chunks. When I say chunk, I mean a particular section of text. So it finds this most relevant piece of text. It based on these n number of texts, it fits into the particular context window, and we tune the prompt to get the response. So in this way, instead of fitting the entire huge corpus of text, we are only fitting in the most relevant parts of this particular document. So let's say in your employee handbook, if someone wants to ask about the number of holidays. So we will not fit everything. The holidays, including the salary slips, the PF, etc. We will only put in the main sections which contain this information about the relevant holidays in the company. So what comprises of this RAG pipeline? So this RAG pipeline comprises of first we have the initial raw document. It can be in any format. It can be a CSV file, a PDF file, a text file, a document file, HTML, anything. And then we first chunk it. What is the meaning of chunking? Chunking simply means splitting this particular raw document. Once we have this text, we split it into raw parts, and then comes the part embedding. Now, what is embedding? Embedding is nothing but simply converting this natural language text into vectors. Vectors are nothing but a certain dimension which contains float values. So once we have so why do we need to convert this particular set of natural language text into a vector? Because any computer or any machine or any algorithm, it does not understand these particular texts. The text is for human knowledge, but these applications or these computer system, they only understand the numbers. So once we have these particular embeddings or the vectors, now comes the part of storage. Now, either we can store it in the computer memory or we can store it somewhere in the disk or we can use dedicated storage systems which are created or attuned to store this particular vectors or embeddings into them, which are called vector databases. And one of the most prominent and open source and completely free to use uh, vector database is Qdrant. So Qdrant, I will again reiterate, Qdrant is completely open source and it is one of the hottest piece of application that is out there right now. And it is on the forefront of open source contribution every time. So it is one of a very great kind of open source product, I would say. And it is also a point that many of enterprise grade applications, they use Qdrant in their production system. So that is something. Uh, and then finally, we come to the point of retrieval. What is retrieval? Retrieval is the uh, procedure in which the user asks the question, we find the most and relevant parts, and then we fit into the prompt and respond. So this finding the n most relevant part of in the text or in the document, that is called retrieval. So in our particular this webinar, I will be using completely open source things and free things. For chunking, I will use regular Python modules. For embedding, I will use open source embedding models, which are provided by Hugging Face. For Qdrant, I'm using local in-memory Qdrant client. And for retrieval, we will again use completely local uh, Python functions. And finally, for if we want to run it end to end, we will need a LLM to generate the responses, right? So for that, I'll be using Hugging Face's inference API, which has a very relaxable free tier limit of 1,000 requests per day. So now we move to the main. Let us discuss about the chunking strategies. So why is chunking strategy important? Because at the end of the day, these texts are going to be stored and to be retrieved by your particular application. So if you provide incoherent section of text, like let's say your one text is saying something else, your other text is saying something else, then it won't really help your application to answer the question at the end of the day. So right now, I'm listing down 5 chunking strategies. The most common one that is used is fixed size overlap. Here we are doing nothing but simply splitting this particular document into n number of chunks, where each chunk is of approximately fixed size. Now, when I say approximately, what does it mean? Here we define the chunk size and chunk overlap. So the chunk size is the uh, number of tokens that we want to have in our particular chunk. And chunk overlap is we can when we are splitting a certain piece of text into n number of parts. Let's say I have 1,000 word character. I'm splitting it into 50, 50, 50, 50. What happens is if let's say your first 50 words, it ends in middle of word, like you were going to say percentage, and it split it, the last character, it came into percent, and the age got left. So when you go to the next section, it will start from age instead of complete percentage. So in that manner, the meaning of that particular section, it completely changes because a word is misplaced. So to avoid that, we use chunk overlap. So what happens is instead of using 50, 50, 50, we go with 50. And then the next 50 will contain the previous, if you are saying chunk overlap of here, let's say 20, then it will contain the current 50 plus previous 20, and then the next 20. So this manner, we are creating an overlap between these particular chunks so that the context, it remains in a more compatible manner instead of splitting in between and losing its meaning in some form. Because at the end of the day, the better the chunk created would be, the better the answer would be. Then come the semantic boundary detection. So what is happens in semantic boundary detection is we scan our particular piece of text to find the uh, punctuation marks, because a sentence in its own makes more sense than a sentence which is being split. Like if a sentence is broken down in middle, that makes less sense because it is not in its complete entirety. So to get these particular full kind of statement so that they are coherent on its own, we use semantic boundary detection. here it may split the document based on the full stop or exclamation mark or question mark, so that it knows, okay, this is my complete entity. I want to save this. So here, why we are using a Hugging Face embedding model? Because whenever using an embedding model, it stores the particular embedding to vector dimension of these punctuation marks. So based on these scanners kind of entity, it is able to scan, okay, this is punctuation mark. We can, instead of using Hugging Face embedding, we can simply use any Python function. Okay, just scan this full stop, split it, mark it, and then split it. So this is how the semantic boundary detection works. The next strategy is recursive structure-aware chunking strategy. Now, this is a very interesting aspect. So let us go back previously to the employee example of our employee handbook. An employee handbook contains different sections and different chapters. So if we are just splitting it between, let's say, a fixed size of chunk, then we don't have a particular understanding about the structure of the text in its own, right? We only have the understanding about the certain words or paragraphs. So here comes in picture the recursive structure aware or markdown header text splitter chunking strategy. In here, we divide this particular piece of text into sections. So let's say I have uh, the employee handbook. It contains 10 different chapters, and each 10 different chapters, we have some subsections. So based on those, we first select, okay, this is my entire section. I will then split it into subsections. And if it also contains subsections, then I will split it further. And along while we are splitting it, we also save this hierarchy on its own. So that way, whenever we use uh, a retrieval mechanism, then okay, I need to find on which how many holidays there are in June. So I will first select, okay, I need to find the holiday section. Then in the holiday section, I need to find the public holiday section. And in the public holiday section, I need to find the June month section. So that way we have a hierarchy maintained, and also we have a very coherent piece of sections to be retrieved later on. The next type of chunking is a parent document chunking. In the parent document chunking, it is a very, it's not, I would say, new concept, but it is one of the most ideally used production grade chunking strategy, in my opinion. Because what happens is whenever you are doing any kind of, let's say, you have a document, right? And you want to create a question answering system. So whenever you convert this particular piece of text into vectors, what it is doing is it is creating a semantic information of that particular text. So at the end of the day, we are going to match this semantic meaning based on our query. So the larger the text, there is a chance that it may have very multiple semantic meanings. Like for example, if I have five sentence paragraph, and I'm converting it into vector, it may contain n number of items like I am going to school, school is good, uh, there was something happened at school, and so on and so forth. So they are different, they are continuous text, but they have different semantic meanings. So it is always a good idea. I would not say really a good idea, but it's a practice that the smaller the complete piece of text is, the more coherent or the singular type of semantic information will be held by it when we convert it into vectors. And then when we do the retrieval part, where we find the most relevant parts, we will we will get the most accurate semantic match or most closely matched semantic part of that particular piece of text. So this is happens when we create the child, or as you say, the small piece of chunk. And then what we do is we store both this large entity and the small entity. So let's say we have split our 1,000 page document into, first we can convert it into 50 pages each. So I have 50 pages, which is a parent document. And then in this 50 pages, I will then split it into one page each. So this will be a child document. So since the child contains the most semantically similar piece of information, I will first retrieve this child thing. And then because this child does not have any context above or before or after it, it does not contain the complete information that is required by our LLM model to answer the question. So what we need is we want the before and after part of it as well. So what we do is we first find the most relevant child vector, and then we find its parent vector. The parent vector contains this particular child as well as a more coherent information which is required or which augments or which supports this child vector. So this is how a parent or child kind of chunking works. Uh, Mind you, these all are available. Everything retriever, the splitter that I'm mentioning, these are available in LangChain, which is an open source entity for free. So you can go over the document, you can check it out. I will also show some hands-on lab on these particular sections. The final piece is proposition chunking. It is a little bit less used, but if you want the best outcome out of all, proposition chunking is the way to go. So what happens is when we have a raw corpus and we do not have any particular sections identified beforehand, we cannot really rely on the fixed chunking, right? Because it contains it. We do not know whether the particular sentences, when we split, they are correlated or when they are not correlated. So in that section, the proposition chunking takes place. In here, we use a LLM, another LLM to first split these entities. So it first finds out, okay, this part of section, these three sentences, they are clubbed together. And the next five sentences, they are clubbed together. They are saying different things, and so on and so forth. So this LLM gives us these particular boundaries for us to store and retrieve it later on. So this is the proposition chunking. Now, after we have created these particular chunks, the next action is storing it into the vector databases. So before we store it into the vector database, we first need to convert it into the vectors. So for converting into vectors, we use something called embedding model. The embedding model are nothing but a particular trained piece of, I would say, an encoder type of model, which converts these natural language text into specific uh, vectors or embeddings which have a certain dimension. So something to note is that each particular embedding model, it has a certain embedding dimension. So in here, I have mentioned 384 because this is used by the embedding model that I'm going to use in the lab, which is BGE3 or BGEM3. And for different kind of embedding models, let's say you use something, another open source called All-Mini LM V6, sorry, L6V2. Its embedding dimension is 256. And if you go something more non-open source, like OpenAI's text embedding ADA002 or text embedding 3 small, it contains the embedding dimension of 1536. So each embedding model, it contains a certain embedding size. The size is what is size is the dimension of this particular embedding model, or it is a size of the vectors that is converted from this text. It does not matter whether your input text contains one word, or it contains 5 words, or it contains 510 words. It will convert it into this particular fixed size embedding dimension. So, uh, and why do we use small and why do we use large dimension? The difference lies between what type of information it is storing. Like if you have a small dimension, it will require less storage to preserve or save, and the retrieval will also be fast. But on the other hand, it will lose some information that could be stored in it. Whereas when we use large dimension models like the text embedding ADA002 kind of models, it contains large dimension, so it will contain more rich semantic information, but it will consume larger space to be stored. So once we have converted these particular text into embeddings, we need to store it in, as I mentioned, a vector database. So right now I'm using Qdrant. So there are many ways of using this Qdrant. Either uh, you, you can self-host it into your particular VM or somewhere. So in that manner, it stores in the disk. But let's say you want to do a small quick POC, then I'm going to use the Qdrant memory here. So what happens is it saves the embeddings into its RAM, but it is to note that do not use this particular memory kind of section of Quadrant into production because it is not persistent. So let's say you do a restart of your system which contains this quadrant, or your system crashes, all the information will be lost. So if you use a persistent kind of deployment of Docker or in K8s of quadrant, it stores it into its own disk file so that it is preserved for later on as well. So once we have discussed about these chunking strategy, and then we discussed about how to convert it into these chunks into vectors, and then we discussed about how do we store this particular vectors into our vector databases. Now comes a very important aspect of this RAG pipeline, in which many of the people falter. It is the retrieval part. So what is retrieval part? Retrieval part is nothing but once we have stored these embeddings or these chunks or these text, we want the most relevant parts. Now, how do we acquire these most relevant parts? So to acquire this, there are different strategies. The most common one of all of them is the dense ANN strategy. This dense ANN strategy is nothing, but we use some kind of mathematical function, like the most commonly used is cosine similarity. So we use these mathematical functions to create the similarity score between the question that we want to ask and the chunks that are stored. And because we have converted these text into the vectors which contains these float or numerical values, we are able to get the most uh, we're able to calculate this distance between this particular pieces of chunks and get the most relevant ones. It works very similar to an unsupervised algorithm like k-nearest neighbor. Uh, so in that manner, we are able to, in our particular vector space, we are able to draw the point. Okay, I have this my question, and I find these n number of chunks which are semantically very closer to the meaning of this particular query. So this is called a dense ANN retrieval, or also the HNSW k-nearest retrieval. It is the most common one, and it is the why does it? And now we ask a question: why does it falter? Since we are going for semantic meaning, why it is not the best option every time? So the answer lies between because this contains semantic meaning. It does not contain the information about the specific words that we are using. So let's say if you have a particular document which contains information about ticket IDs. Now ticket IDs, they are of specific format, like let's say it's of the format TC1234, TC2456, TC3897. So at the end of the day, these dense ANN models, they are first splitting these particular entities into different chunks or into different tokens. So it will split this TC, ABCD, TC1234 into TC and ABCD, TC into 1234. And now, since we're using an trained embedding model, this embedding model does not contain the information about what is TC. It has no idea. So whenever we ask a question about, okay, tell me about TC1234, it will find the semantic, it will search for semantic meaning, and it will say, okay, TC1234, TC ABCD, TC3987, they all sound similar. So that's why I will give these options as the most optimal one, even if it does not contain the specific word TC1234 that you want to search for. So to resolve that, we move to the hybrid BM25 plus ANN architecture. So what is BM25? BM25 is best match 25. It is very similar to, since you're all knowledgeable people, you must have heard of TF-IDF while you were working in this AI or machine learning sections previous on. So BM25 works similarly to this TF-IDF. It contains uh, it, it contains a calculation or score matching based on the keywords or words that are introduced. So this BM25, it gives more preference to the words that occur in our particular chunk rather than the meaning of the chunk. So this rank BM25, from this we are able to get the most n number of sections which contains the particular words that we want to search for. And again, why? a BM25 complete is not a good option on its own because it is not because at the end of the day we are asking a question which is does not which only contains a certain keyword that we want to match for, not the most common ones. So let's say if you have asked for uh, an article the is very commonly present everywhere. So it will try to find the most number of the options and it will return me back, which I do not want because the is an article. It does not contain a semantic meaning at all. So what do we go for? We go for a hybrid BM25 plus ANN. So ANN is the previous one, the dense ANN semantic meaning part, and BM25 is the word frequency part. So we give so here what we do is we create something called an ensemble retriever. This ensemble retriever, we give both, okay, use BM25 as well and use dense ANN as well. And we give it a certain weights associated with these two retrieval patterns. Now, what is weight? Weight is nothing but simply we want to tell the particular retriever that, okay, give more preference to this. If we set higher weight to the BM25 part, let's say out of 1, we give zero point 0.8 to BM25, zero point 0.2 to ANN. It will prioritize finding the keywords more rather than the semantic meaning. And if you give BM25 less, let's say 0.25 and give ANN more, 0.75, it will only search for certain keywords in its own, but and then prioritize the semantic similarity matching. Now, what happens behind the scene is that when we use this kind of ensemble retriever, it does both separately. It first retrieves the top n elements from BM25, and then it retrieves the top n elements from ANN. And then, based on the weights that we have assigned, it creates a cross mapping to get the most common one out of them, and then creates a final score. So based on those final score rankings, it returns us this particular set of chunks which it deems the most relevant. Now, what happens uh, if, let's say, you have five different chunks that is being retrieved, both from dense AI and hybrid BM25, which are very, let's say, not close in meaning. It is to note that whenever we are creating these vectors into embeddings, when we are using these cosine similarity techniques or this calculation techniques to find the nearest n neighbors, it does not store the information about the direction. Like, because since we are going for the k nearest neighbor, it can be in any direction, right? So let's say I have five documents which contains the word uh, I'm going to eat banana. I'm going to eat apple. I'm going to eat snacks and so on and so forth. And if someone asks about banana, and yeah, let's say where can I eat banana? Then it will see okay, he asked about eat, and because these banana, apple, these all are fruits. The semantic meaning of these banana apples are very close to each other because they are eatable fruits. So it is very much possible that it will not return this banana part, but everything that it encompasses in it, whether it is banana, apple, or any kind of snack, because we talked about eating. So here comes in the BG re-ranker. Why do we need re-ranking? So this is why we need re-ranking, because it does not contain it contains the semantic information, but the semantic information is not exactly matching our query because it just shoots in the dark, gets the top five closest one, and returns back to us. But we need the most relevant ones which are able to answer our question. So these cross-encoder models are trained in this aspect, in which it is given top k elements to decide from and a query, and it is trained to select the top and most relevant ones to answer the query, not whether they are close to each other or close in meaning to each other. It is being ranked based on how much it can better answer the question of our own. So this is how a cross-encoder re-ranking model works. And then the final part is MMR, which is maximal marginal relevance. It is relatively less used, but it should be used in production system as far as I am concerned about. Because what does it do is, let's say you have a particular piece of document. It contains the five sentences in different section of your document, let's say five times a particular text which appears five times. So when you ask about something, your particular dense AI hybrid BM25, it finds, okay, this is the closest meaning. but then it also occurs once again. So it will also say, okay, this is also very close. Third time, okay, this is also very close. So if you are going for top five most relevant items, it will return you the same meaning sentences. They may be augmented a little bit because since we are going for the semantic meaning, it will give us the five almost same sounding sentences back to us for answering the question, which is not really desired. We want some diversity in it. So to counter that, we use MMR. What does MMR do? It calculates the distance between the retrieved parts, and it tries to get some diversity into this. If it first scans all these retrieved chunks, okay, and then it detects, okay, these are very similar sounding, or they are very close to meaning of each other. So we do not want that. So it will discard one of those. It will take in another and again find the particular section. So that way we have a diverse set of information which we can provide it later on to our LLM model to answer the question. So this is how the hybrid retrieval works. We create a BM25 retriever. We give them, okay, find the top 10 chunks which contains these words more. And then I have a vector database. Vector database find 10 words which have closest in semantic meaning. Then we assign weights and then we get the particular final set of chunks that we want to retrieve. Everything that I mentioned, it does in behind the scenes. Same for BG Ranker, we use a cross-encoder model. This particular by BG Ranker base, it is completely open source. It can be found in Hugging Face, hosted there. So you can download it locally and you can use that. So here what it does is it first takes in the candidates, which are the chunks, and then it loads the model and it predicts based on the query that we have that we want to ask, how better they are in a position to answer our question. Based on that, it returns the scores, and then we can take top n or top k or then sort them accordingly based on the responses. Another point to note is that whenever you are using prompts or this RAG kind of implementation where you store these chunks into your prompt window, it is to note that this particular LLM models, they have a U-shaped memory management. Uh, so what happens is that any kind of piece of information that you store at the starting of the prompt, at the end of the prompt, it is given more importance by the LLM model compared to the information that is stored in the middle of the prompt. So that's why it is always a better idea to store these chunks, the most based on this sorting, the most relevant pieces of chunks to the top, and then we skip them to the middle as in the lower priority of how they score well in this particular re-ranking. So now we have discussed about everything, the entire RAG pipeline from start to end. The start is chunking strategy. After chunking, we convert it into embeddings. For embeddings, you can use any kind of embedding model, whether it is open source or closed source. Then we store these embeddings into vector databases. Open source part is called Qdrant, as I mentioned. And then after the Qdrant, using the Qdrant, we'll retrieve these embeddings based on our needs. And then finally, we prompt it into our LLM and we answer the question. So before we go further, let's go over some of the labs that I have prepared quickly. So this first lab, it is of the chunking comparison. So here, let me first install some dependencies, and then we will import the models. So here right now, for a piece of document, I'm using possibly one of the highly coveted and most read research papers of the 21st century, which is Attention All You Need paper, which discusses about the transformer models. So we load this section, and it is to note that whenever I talk about the chunkings and the number of elements, we are always talking about in terms of tokens, not words or not characters. Why? Because at the end of the day, the LLM, it first tokenizes the particular piece of text that you provided. And then based on those particular pieces of text, it converts it into particular tokens. These tokens are numerical entities. So the length of the particular model that it can fit in, it is all based on the tokens and not characters or words. So once we have loaded this particular tokenizer, this is the fixed size with overlap. Here we use recursive character text splitter from LangChain. We just simply load the text and then we provide 150 chunk size with 20 overlap. It gives us 132 chunk, 150 chunk. Got it? So based on as you can see, the average is it created 5 chunks from my document, which the maximum chunk size is 150, and then it contains chunk overlap of 20, as I had mentioned previously. You can also provide the separators if you want to give, okay, you should always put in new lines. So that's why the number of tokens in this chunk is small because it found this one of the new line characters. So that's why it's split there on. If there were no new line characters, we will always get the chunk size as 150 fixed. And this 150 fixed, it includes the overlapped values as well. So now we move on to the recursive structure aware. As I mentioned, this is one of the highly used ones. And this is to be used when we are aware about the structure of our document. Like we know beforehand, okay, it will contain this heading, it will contain this subheading, it will contain this subsection. So we load our recursive markdown text splitter and we tell them, okay, this means section, this means subsection, this means subsection. And then we use a text splitter to finally get this particular chunks. Now, to note that when we are storing these chunks, we also store the metadata. This metadata, using this metadata, we can create knowledge graphs and we can use tree structures to be used later on in our document if we require it. So let's say I want to study about the history of machine learning or history of attention. That will try to find the history part and then okay, it will check, okay, this is the history part, but what it is part of? It is part of the attention mechanism. So this is how the markdown retrieval works. Once we have created these chunks, we store it into our Qdrant vector database. Here I'm using memory. So if I restart the system, every vector that I have stored, it will be lost. So if we are going for production system, always use in-disk memory. It is better if you can get SSD into that particular VM where you are hosting this Qdrant, or HDD works quite as well. In this, we give a collection name. A collection is nothing but a collection of these vectors that we want to store, which are of same nature. So if you want to do some kind of searching, we will do the search in this collection, which contains a similar set of information that we want to retrieve. Then you provide the vectors configuration. The size, as I mentioned, is the size of the embedding, the size of the or size or the embedding dimension of the particular embedding model, and this distance is the uh, uh, a calculation or a function that or a algorithm that we are going to provide to this embedding model to get or retrieve the top and most relevant chunks. So here we're using a cosine similarity to get the n number of not really n, I would say here right now because it comes in the retrieval part to get the nearest neighbors of the particular query. So then we create a Qdrant vector store, and then we store all our chunks that we had created previously into our Qdrant collection using simply store.add documents. So we created two collections. One is fixed using fixed chunks, which does not contain any kind of metadata information of section or subsection. And second is the recursive part, which contains this information about the sections and subsections. So once we have done the indexing, now let us test some queries. How does it perform? So as you can see, whenever we ask a question, like what is the scale dot attention and how it is computed, the fixed size gives us the 150 character because we created of that. But the recursive part, it gives us a section. It finds, okay, I need to find for scale dot product attention. I see a section which contains the information of scale dot product attention. So it will retrieve this particular part. And along with that, it also mentions, okay, the subsection is scale dot product attention. What it is part of, it is part of self-attention, and it is part of the attention mechanism and on its whole. So these are the two most relevant or most commonly used chunking strategy. This MR retrieval that I mentioned about, where we want to create some kind of diversity. So here you can see when we go with plain retrieval, it gives us when we ask about attention, it gave, since we mentioned here dot product attention, it found out all three which contains these words called attentions, whether it is self attention or it is multi-head attention or it is application attention. But when we enforce the diversity, it is able to give the self attention and it found out, okay, multi-head attention, it sounds very close to self attention. So I need to go with the encoder. So it has more diversity at the end of the day when we provide it to the LLM for generation. And then we move on to the parent document retriever. As I had mentioned, this is one of the hottest fields that is being used in production right now all over the enterprise because in this way we are able to find the closest match, semantic closest match in semantic aspect, and then we are able to provide the rich context which contains the pre and the post and the prior, and so that it has all the information surrounding it beforehand. So once we have, uh, I will again load the same file and then we are going to store it into our memory. So here, as you can see, I've created two splitters. One is a child splitter, which is of small chunk size of 80, and the other is a parent splitter, which contains large chunk size of 600. So in this particular parent splitter, it contains all these child splitters. Since we are using this parent document retriever, here we provide the child splitter, the parent splitter. Why do we need doc store? We need doc stores to create these particular mappings of child and parent. And then the vector store is our quadrant vector store, as you can see. We store it, done. As you can see, the child chunks based on a particular section in our attention paper, 11 chunks were created of child and two big chunk were created of parent. Let us see the comparison between them. As you can see, child chunks are small and precise. Decoder, multi-head transformer. And then the parent document, it contains all the particular section, all the information, which is part of this particular part. So this is a plain store that you want to see for comparison. And now let's see. If we complain this plain store and versus parent doc store, how does it go ahead? So you can see the difference. When you ask about what is scaled for dot product attention, it only gave me the formula. But when I go for the parent part, it gave me the prior information about what is attention. So let's say if anyone naive come to, if you have built this question answering mechanism and any naive person comes to it and asks for a particular piece of, let's say, an item, then if your LM only has the information about the particular part, it will not be able to answer the question in its entirety. It will not be able to help the person more. But if it has all the information encompassing it, it will be able to help the better the user. So now let us check if we ask a question and I want to see if these particular keywords were captured by my retriever or not, because these keywords are important for answering my question. How does a parent doc retriever and a pure plain fixed size chunking retriever fare? So as you can see, out of all these keywords, the plain retriever was able to only find 6 out of 7 words, 3 out of 5 words, and then it scored 100% in the rest. But the parent doc retriever, it scored 100% all the time. So in this manner, whenever we are using a chatbot or we are creating an application which helps in question answering, the parent contains all the information. And now when not to use this parent doc retriever, it is when you have to have the context window in a very focused manner. If your context window, if you give a lot of information to your context window, it may crowd it and it may create some kind of bias, or it may lose information to be answered beforehand. So there is no one rule fit to all the parts. You have to think about your application. You have to think about, okay, when this can come relevant, when I need more encompassing information, When do I need more focused information? When do I need more keyword oriented information? So we use these particular chunking strategies, these particular retrievers accordingly. Now I will show you the hybrid re-ranker, again using the same piece of document. So here we create a BM25 retriever. BM25, as I mentioned, it contains the information about the keywords or the words that we are going to use. So for creating that, we create a hybrid collection. Why we are using hybrid collection? Because we are using both BM25 retriever as well as the dense retriever. So this quadrant vector store contains, it stores both the information now. Here we have splitted the information. We created the vector store, and then we will ask the question, what is scale dot product attention? Then now it was able to find, okay, scale dot product attention. It is using the words attention and product more. So it finds out, okay, I need to find these particular words which are present, and I will give them a little bit more priority. And then I will also find if it has similar semantic meaning, and then I'll find the top based on the cross mapping, the score, what are the top most relevant parts. And now we come to the BG re-ranker. As you can see, I have loaded the cross-encoder model. This is an open source model, BG re-ranker based. One of the most famous models of re-ranking is, as you may have heard, the Cohere models. Cohere provides this cross-encoder models which are very high quality, but BAI has also open sourced some very highly performing cross-encoder models. So when we use this BG cross-encoder, uh, it is first loading it into the memory for inference, and then it will first retrieve the top uh, whatever we have mentioned here in the retrieval section, those top k elements, and then it will try to find based on the, as I had previously said, it will try to find based on my query which chunks of these contain the most important information, and then it based on that it gives us the score. So as you can see, I asked a question uh, that I had previously asked in here. What is scale dot attention? It is now able to find, okay, this self-attention part, it contains the most relevant information for me. So it gave me a score of 0.99. So we can also use some kind of scoring filtering. So once we have, let's say from our uh, uh, quadrant vector store, we have retrieved the top 20 chunks. So we then move on to the re-ranker, and we say, okay, I will only need the top 5 most relevant chunks which have a higher score than, let's say, zero point 0.8. So even if only one item has a score of zero point 0.8, it will give me the single most important chunk or the vector to be stored later on or to be used later on. So this is why we use a re-ranking mechanism. I hope that was clear. And then finally, let us check how our entire BM25 plus a dense architecture. And then when we use the BGD ranking, how does it go well, or how does it work when we are using it in an inference? So I asked the question, who introduced attention and when? So it was able to find the top and first based on this ensemble retrieval, the top and most relevant parts. Then it created the using BG, it re-ranked those particular chunks, and then it finally gave. I entered into my context window in here, as you can see, answered the question based on the context. And I have used an open source model, Qwen 2.57b Instruct. Again, it is available in Hugging Face. And when we're using inference client, uh, if I create an Hugging Face token, which is free to create, I get 1,000 requests per day. So you can use in your demo or POC application as much as you want. So as you can see, it answered my question quite accurately, as was mentioned here. So let's say we run all these 5 queries now. Again, it will give me, after ranking, the top score and the answer. The top score and the answer. So now we have discussed about the entire RAG pipeline. How do we need to use it in production? When to use what? So once you have trained this entire RAG application, now comes the most important part, evaluation. Because without evaluation, you are just shooting in the dark. You do not want to move your items into production without knowing how they are working, how well they are working, how bad they are working. So to create these evaluations, we use open source uh, models or the sections which or the open source application which is called ragas. So this what does ragas do? Ragas is it contains some certain scoring mechanism for these particular parts, whether it is faithfulness, relevancy, context recall, and precision. And how does it calculate? It calculates by the because we provide an LLM for it to calculate. So here we first create a LangChain wrapper, in which wrapper we give it a LLM application. Okay, you use this judge LLM model, LLM as a judge model, to evaluate my questions, my answers, my ground truth, and my retrieved chunks. So we simply import from Ragas the evaluate function. We provide, okay, I need answers in these matrices, and you use this embedding model to get the retrieval section going on, and you use this judge LLM to get me a validation of how well my entire RAG pipeline is working. So let us run the Ragas evaluation here. Here I'm using the Qwen 2.57b instruct model for answering the question, as well as for creating a judge LLM as a judge. So what I've done is, from my previous top 5 questions, I have stored the question, the answer, the retrieved chunks as context, and the ground truth. The ground truth is the answer that I want, as mentioned here. This is the question, this is my ground truth. So based on my ground truth and my answer and the context that I retrieve, will create a report for me. It will create a report. Okay, how well this is working, how high it scored in faithfulness, how relevant were the answers, and how well was the context recall. So currently the inference is going on because I'm using an open source model. If you use some closed source model like OpenAI or Anthropic, you will get answers faster. So tada, we get the score. Okay, based on my question and the chunks that I retrieved from my retriever model and the answer that I generated from my LLM model and my prompt, I was able to get, okay, the answer was very faithful. The answer was very relevant. How relevant was the answer and how well it was able to get the context recall based on the chunks that I have retrieved. So this evaluation is one of the most important aspect whenever you're going to production. It is always better when you go into production to create some kind of cron job which runs every n number of hours. Let's say it runs every 6 hours. It will execute this particular set of questions and it will give you an evaluation report. So let's say you have hosted a production application using GPT-4o, ChatGPT using GPT-4o model, and GPT models they did something in the architecture that the answer is not coming well right now. So if you have this cron job of evaluation running, you will immediately see, okay, the answers are not generating quite well. Or if you wanted a JSON response, it is not able to create that JSON response schema. So it will immediately flag, okay, your evaluation is going down. You need to quickly fix it. You can make the adjustment in the prompt or in your architecture and then redeploy. So this kind of evaluation and alarming mechanism should always be present in your production systems. This was my entire stack summary. Now we go to the some of the normal points. Why do we need normalized embedding? So when we convert any particular, okay, my bad. When we convert any text into vectors, the it is very important that these embeddings they vary from each item in the particular vector. It ranges from -1 to +1, because if they do not range from -1 to +1, the particular function that you use, it has no way of getting the top and most relevant score. So it is always important that to vectorize, whenever you're vectorizing, you normalize your embeddings, and then always ensure that your vector dimensions are correct. If you have stored your vectors in your vector database with a particular model with a particular dimension, always use that particular model and that particular dimension when you are doing the inference as well. Because if there's a mismatch, you will not get the correct answer because they store different kind of semantics in different format. So that's why it is important. Uh, Rest I have already gone through. So when to use different chunking strategies based on your document. If you have a very structured document, go with Markdown head retrieval because it gives us the sections and subsections as well as the entire knowledge graph or structure tree, which is quite important. When you have a very long form prose and you want to split it into some self-contained facts or self-contained group of text, then you go with semantic chunker. When you have when you need the best precision plus context, okay, I need this most accurate uh, sentences as well as the underlying concept behind it or the context behind it, then we go with parent document retriever. And then when we want to use, okay, I have this piece of information and then I do not know how to best chunk it, but it is very important that the chunking is very coherent. Then we go with position chunking where we use any LLM model to tell it to, okay, generate these sections and I want this information. And then when you have no idea, go with the recursive text splitter. It is great for POC. And in but when you go with production model, I would say try to avoid this particular simple fixed size overlap. Always have a particular section in your mind when you're going for it. These were the particular open source tech that I used. LangChain is completely open source. For embedding model, I use bias models. They're Apache 2.0 licensed. Qdrant is also Apache 2.0 or MIT license, so you can use it for free every time. RangBM25, pure Python, can be used anytime. The cross-encoder BAI models, they are open source and they perform quite well. If you want to go for closed source, Cohere is the best option. But again, open source models, they are available to us, which perform quite great. For at the Hugging Face Inference API, as I mentioned, 1,000 requests per day, free tier. You are well to use. Uh, and if you want to go with OpenAI or Anthropic, feel free to do that, or Gemini. And then Ragas, this is simply a Python module. So you can install it and use it anytime. But the underlying LLM models that you have to provide, whether it is open source or closed source. So these were the key takeaways that I had talked about. So that was all really from my side in this webinar.